Okay, this is TempleOS 5-minute random code walkthrough, episode 69. And I'm your host, Terry Davis. Looks like God took us to the compiler. And it looks like, well, we've already covered this routine one time. Okay. This is in the compiler when it's okay. So if we say otrace on, that turns on the optimizer trace. The optimizer has about 10 passes. Anyway, if let's give ourselves if I greater than 0 and j greater than 0, true. I don't have a lot of warnings. So what we have here is when it parses the base pointer, 8 off the base pointer is I, dereference I. This uses a stack machine, so it adds -8 and base pointer. Then it pushes a 0. Then so this sitting on the stack at this point is a 0 and the dereference value of I. So we have I and 0. Then we have a greater takes all of this operation, pops 2 pushes 1, this pops 1 pushes 1, this pushes 1, this pops 2 pushes 1. Then we have so this is on the stack at that point. Then we do the same thing, and then we take this and is operating on this greater and that greater. So if the and is the greater operation is a logical 1 or 0 result, 1 or 0. Then we do and we push the logical 1 or 0. Then we branch if 0. So this is it starts out RISC, and then all the purpose of the optimization is to make it CISC, more or less. As it turns out, the CPU puts it back into RISC, and so these optimizations don't really help it much, which is kind of funny. You know, someday when somebody is holier than I am, they can follow the true spirit and get rid of some lines of code, because lines of code is that's our highest goal, is to remove lines of code. So we can get rid of all the optimizing. It's not quite true, but anyway. So yeah, naturally I thought of a stack machine CPU, but I'm not gonna. That's for losers. Make up CPUs. You fight the war with the army you have, not the army you want. There's other issues, but anyway. So let's see how we're optimizing. Okay, now at this point we have combined the greater than into a less than or equal, branch less or equal. So this branches if 0 after the whole thing is done. So there's only one branch, and that's at the end. Now at this point we have if you branch, that's the false. So that's why we have an inversion. That's why this is the opposite. So we branch if less or equal. And we have short circuit logic. So we have 2 branches. So if the first one is less or equal, or the second one is less or equal, it's an and. So anyway, so I can also show you a different thing, which is 1 less than 5, let's say this. So this is coded as 1. There's then this is, it pushes a 1, it pushes that, it does a less than on that. Then we start getting into the push compare. This pushes the middle term. Oops, I made a crazy thing. It didn't mind. Anyway, the middle term is shared, and so the middle term can be an expression. So we push the result to the middle term expression, and at this point we're doing branch greater, and then we do an and. So the two comparisons, this greater and this less, are and-ded, and then the result branch 0. So there's a second version of branch greater equal. Now this gets into this crazy push thing. Sometimes it literally pushes, and when you literally push, you have to clean up the stack in either branch situation. Anyway, other times it uses a R. If you're curious, I think it uses a RCX as the pushed value. It's not pushed, it's stored in. Sometimes instead of pushing, you can use a register if it's top of the stack. So let's see how it coded this. It's not smart enough to know that it's always false. That's just, it's stupid making a compiler optimized for stupid programmers. If you have it, just write the code like an intelligent programmer. Don't make the compiler bloated because of retard programmers that don't exist. Anyway, so what do we got here? Compare to 1. So RSI, that must be the I variable got stuck in a register. Branch less or equal, move 5, compare RAX to 5. So it moved it into RAX. I was wrong about CX. Where did it do that optimizing? I don't know. Anyway, so getting back to this routine. So this routine is this combines together a lesser equal or a greater equal is this pops 2 off the stack, pushes 1, and the 1 is it's either a true or false. So that's what these logical operators do. And then if we get a branch 0, what is I? Is it the previous one? I is the previous one. So coming into this, we're handed the branch 0, and we find the lag. We precede this. All it is a circular queue. So we just back up 1, and we learn to skip. Sometimes we have to keep the stack intact, and so you have no ops that a no operation. Some of the no ops pop the stack, the figurative stack. Well, this is when we are simplifying. Some people think this is interpreter. Well, when you simplify, you do interpret. In fact, if you simplify an expression, the compiler interprets, and then it codes a simplified value. So we are simplifying, combining together a logical and a branch. And the interesting thing here is if it's a not, then it inverts the logic and calls the branch not. What does it do? No, it no-ops it. Doesn't it no-op it? Wait a minute. Free is the same. Okay, we don't no-op. We free it. It used to just no-op them. I had an array, and it had to make them into a no-op if it was simplified. Now we free it because it's not an array. It's a circular doubly linked list that's malloc. Anyway, so there's a companion routine. This is branch 0, The companion routine is branch not 0. And these will, if you do not, it will simplify those right here. And anyway, so the other interesting thing to note here is we have bit test and set, bit test and clear. These operations are intrinsic. I don't know what you want to call them. I don't have any inlining, but you can add functions to the compiler that are intrinsic. The bit test operations are really well coded. Those are one of my favorite. I love bit operations. I'm only interested in Intel architecture. Anyway, so the bit operations are done as a call to the bit test or bit test and set, locked bit test and set. So that's a little bit different. So we do a branch if bit test and set. So we're making it into sysc. So we combine together a bit test with a branch, and that's how we get this. So anyway.